That's a great talk, and thanks for the questions. Our next speaker is Ben Hu from computer science. We know that interpretability is one of the broad aims in the scientific machine learning program, and Ben's been working on both automated machine learning and aspects of interpretability in that. So, Ben, please proceed.
Sure. Thanks, Nick, for the very nice introduction. And today I'm going to talk about automated machine learning, and especially the efforts how we develop AutoML systems. Again, my name is Ben. I'm currently an associate professor in computer science department. Firstly, I would like to give you a brief introduction about what is AutoML, which is to make machine learning, especially complicated machine learning models or deep learning models, accessible to people with limited machine learning background. They could be domain experts from different application areas, or they could be also very experienced data scientists, such that automated machine learning would enable them to have a very good start in their own exploration. And the key idea is to automate the end-to-end process from the data to the results. Traditional machine learning is like we have a data, we try different combinations of pre-processing, feature engineering, and we select the right machine learning model, and we try multiple rounds, as well as hyperparameter selection and parameter training. And especially recently, deep learning has been criticized of lacking the theoretical foundation, and we don't have a good interpretability. That's why in many cases, we will just try and see how it works. And here, AutoML is like to build up this black box such that we just give a data, and we will do all of the search space design, working with domain experts, as well as we will try to accelerate this search process, such that we are able to provide a competitive machine learning model with selected hyperparameters, and which will be very competitive comparing to other manually tuned baselines. In general, AutoML systems can be divided into these parts. The first part is like giving a specific application. We have to define the search space, meaning that we already had some a very good understanding of this domain. For example, for text classification, traditionally we have some naive Bayes classifiers, and we also have some deep learning models. We already know that some of the models historically they have had a very good performance in this area. That's why we want to work with domain experts, work with some data scientists to specifically design the search space. The second step is giving the defined search space, how we can really have an efficient search. And based on the output from this search algorithm, for example, we have decided, okay, we will go for a CNN. And we will go for a very specific architecture, and we will select these parameters to start. How we can really evaluate to validate the performance of the outputted deep learning model or machine learning model in general. So that's why the whole process, it can be divided into generation, observation, and update, the 3 steps. And today I'm going to show you how we design the AutoML system for deep learning specifically. And I will just very quickly introduce 2 recent applications for AutoML to deal with recommender systems and outlier detection specifically. Okay, the goal of AutoML system is the input will be a data set. We only have a very rough understanding. We just start our exploration. And we know historically some of the data sets, they work very well on image data. Some of them they work very well on network data. That's why we build up this black box. And the output will be the recommended model, which can be used for domain applications, and as well as the corresponding predictions to the testing data. So this is the input and the output. And our goal is to achieve competitive performance comparing to other baseline methods. And again, this is a 3-step we just introduced. And the whole point here is like how much time we have for outputting an effective deep learning model. And going through this loop, many times we are able to try different combinations of the models, hyperparameters, and we are able to train train many specific models such that we are able to make the prediction. That's why the whole exploration process would be roughly the time complexity approximately will be big O n t. Here t represents the average observation time, meaning like going for each iteration, how much time we need, and n represents number of iterations we need to go through for a good solution. And here there are two problems we need to solve. The first problem is like the search algorithm. In many cases, there are some algorithms have been designed, such as evolutionary algorithm, reinforcement learning. The problem is like they need to go through the neural architecture search loop many times, too many times. And another challenge is like, as we know, even though we already know we want to make use of one neural architecture, still training the deep learning model from scratch, it takes a long time. And even training one model is pretty time consuming. That's why these two challenges make our time consumption is much, in a very bad situation. That's why how to deal with the challenges to make sure we will go through the iteration as less as possible. That's first. Second, we want to make each of the evaluation as efficient as possible. That's the whole point of designing this system. So we give out our solution. Here is a very basic introduction about, so firstly, we make use of Bayesian optimization, try to accelerate this exploration process. We only need a very few iterations to converge to a local optimum. And the second is like, we want to make sure each training of the deep neural network, we will have a very quick approximation. That's why we make use of a technique called network morphism, which will, the basic idea is to make use of the weights in trained architectures from our historical data. We don't have to train the deep model from scratch for each of the observation, such that we are able to have a very good approximation of the performance of the outputted architecture. Specifically for Bayesian-guided network morphism, which was proposed in AutoML, which is our published system. And here the key idea is to propose a new neural architecture search method based on Bayesian optimization and network morphism. As we can see from the figure on the right-hand side, it shows how we explore the points. So each observation represents each iteration in the search loop. So at the time step 2, we have 2 observed points, meaning that we already evaluated 2 neural architectures, outputted neural architectures, and they have been stored in our historical log. And based on the observation, we are able to approximate the distribution. And based on the acquisition function, based on the utility function we designed, we are able to decide what is the next point, which will provide us the maximum information, such that we can approximate this distribution in a better way. That's why, given this point identified by the utility function, we are able to decide the next point at the time step 3. That's the x3 we want to observe. We run one more evaluation, and then we will have 3 points observed. Based on more and more observations, we are able to approximate the distribution better and better. So based on this approximation, we are able to output the architecture corresponding to the maximum performance. So this is the basic idea how Bayesian optimization could be used for neural architecture search problems. And another problem, as we discussed, every single time, we have to train the neural architecture from scratch, which is extremely time consuming. That's why we proposed, how about we don't train it from nothing? We just, based on some historical data, based on what we have done before, we just store all of the weights, and we only deal with the newly modified components of the deep neural network. So here we propose the 3 different types of actions we could do in the system. So firstly, based on the original neural network, we are able to make one of the layers wider. We can add some more layers or more components, and also we can add skip connections. Based on these 3 basic operations, we can significantly accelerate the approximation of the weights of these trained networks. So based on Bayesian optimization, based on network morphism, that's a basic like algorithm designed for the system. Also, we have very carefully designed the system and support user call from the API, and the Bayesian search part is supported by GPU, and the training of the neural network will be done on GPU. That's why we are able to support the parallel computing by utilizing both CPU and GPUs. I mean, this will somehow maximize the resources we have at hand in the lab. And also the search models will be stored on a storage device. They will be easily outputted as a Keras model or TensorFlow model, which can be used for fine tuning. Especially we already have some like, if just in case we already have some like data scientists in place for the application. And GPU and CPU computation can be run in parallel, and the searcher passes a neural network to GPU for training, and also we just run Bayesian optimization for the search process on the GPU. And by comparing the proposed AutoKeras system with other baseline methods and packages. So we conducted the quantitative evaluation to compare the system with some simple methods such as grid search, random search, and also some traditional AutoML solutions such as MAC and SPMT. And also we compare the algorithms with the state of the art, which utilizes the reinforcement learning or EA algorithms for the search, as well as some variants. What if we only use network morphism? What if we only use Bayesian optimization? So would those like systems work? From this table, we can see while AutoKeras already achieved a very good performance with system optimization, the AutoKeras deployed version achieved a much better performance comparing with other baselines. And also, as we discussed in the beginning, the efficiency is one of the most important concerns for AutoML. That's why we compare the time consumption to see how much time we need for each of for outputting one model or more. So from this table, the blue line represents the AutoKeras deployed version, and it achieves much lower error rate, giving a fixed number of models, and it is much faster than some other deployed version. In addition to the algorithms and the design, we have also open sourced this system. You can simply search AutoKeras on Google. Currently, this is the mostly used automated deep learning system on GitHub, and we have received 7,000 stars and over 1,000 forks. It has been widely used by industry, by many leading companies for AutoML. And we have also teamed up with Google to push this as the open source AutoML deep learning system for Google. Yeah. So in addition to general, as we can say, AutoKeras is a general automated deep learning system, which provides a lot of functions and flexibilities for people to use. In addition to that, still efficiency would be a significant concern for many downstream applications. That's why if we are able to team up with domain experts, if we have a pretty good understanding of the search space, we are able to do this system in a much faster fashion. So based on this philosophy, we specifically designed systems for recommender systems and outlier detection. And also we are working with several other teams to develop tailored solutions for their engineering and scientific applications. Here we show an example of automated recommendation, which is a very, very complicated task and which is considered as one of the major revenue sources of internet industry. And as we can see, for recommender systems, we have many different types of objectives. Sometimes we wanna make the top 10 hits, or sometimes we just want to minimize our MSE. So we have different types of objectives, and we have many different types of algorithms, feature interactions, and we are facing very heterogeneous data, tabular data, network data, user profile data, and text data, many different types of data. How we can really do this? And recently we published a paper about automated recommender system, and also we open sourced the system, just in case you are interested in that. I'm not going to dig into the details. Another problem is automated outlier detection. As we know, outlier detection is to identify the data instances which will be different from the major distribution of the data. And this has very wide application in cybersecurity, in manufacturing, in many safety related applications, and so on. So existing NAS, neural architecture search methods, are unsuitable for automating outlier detection because they simply ignore the properties of outliers, and the data is super imbalanced. As we discussed, if we have a very good understanding of the problem already, we are able to develop a much more effective and efficient system for dealing with problems, because essentially we can narrow the search space, which will significantly help the system design and development. So outlier detection, similarly, we are facing the problems like for a domain experts, we are facing too many different types of outlier detection methods. We don't know which one to use, where to start, and how to deal with heterogeneous data. And yeah, there are many very specific problems to deal with. And for automated machine learning systems, we are able to formulate all of these as our one of the search items. And so our goal is to consider outlier definition in search and the data distribution. And we are able to search for definition hypothesis, which decides the objective function. And we are able to explore untaped search space and exploit useful past samples. In conclusion, here today, I gave a very quick introduction about our system, AutoKeras, as well as some algorithms behind to support AutoKeras system design and development. Also, we showcase that we have a lot of possibilities for extending AutoML in downstream engineering and scientific explorations, downstream applications. And we are very open to any collaboration with domain experts team for developing downstream tailored systems. And finally, I would like to thank all my students in the data lab, as well as funding agencies to support our research from federal agencies and industrial partners. And as Nick introduced in the beginning, in addition to automated deep learning, automated machine learning, in my group, we also have another research direction, which is explainable AI, which is to understand how the system works, how the algorithm works, how a decision is made in such a way. So the vision for me to develop machine learning systems is I want to really bridge the gap between complicated machine learning systems with our end users, with these two extremely different research direction. One is like to build up this black box, which can be easily utilized by domain experts. This is automated machine learning. We don't need any extra input from the end users. 3 lines of codes for AutoKeras solve the problem. And another line of work is like XAI, explainable AI. We try to open this black box, try to make this black box transparent to our users, such that our end users can understand the system, understand the algorithm, and make this usable in many applications which need interpretability. Okay, again, I'm pretty open to any collaboration opportunities, and thanks very much. Any questions and comments are very welcome. Thank you.
Hey, thanks, Ben, for an interesting talk. If people have comments or questions, please feel free to ask directly or post in the chat.
Okay, where's the chat? Let me see.
So I have a question. This is a Jen talk. I have a question.
Hey, Jen, yeah.
Hey, so just first one comment for those of you who are not familiar with AutoKeras. AutoKeras is one of the most popular AutoML packages, and for not just the Keras community, a lot of users now in the TensorFlow community are using AutoKeras as well. So as you can see, Ben just mentioned, just show the slides with on GitHub. It's it's a very popular package. So my question is, for a lot of work involving scientific machine learning, we'll be likely using, calling probably the AutoML packages, from either C or Fortran interface. Do you have any plan to provide, say, C++ interface for AutoKeras, or AutoML package itself, not AutoKeras, at a high level, but probably based on your lower level implementation?
Yeah, unfortunately, we are overloaded, and we don't have the plan for the near future for a C++ version. Yeah, at least not for the next few months, for sure.
No, definitely not the next few months, but yeah, I think it probably is just something in the long term. Right?
Yeah, not for now, at least. I maybe if we can get some like large support from some like agencies, maybe that's possible. But I mean, otherwise we don't have the plan to extend it to C++. That's a lot of work. Yeah.
Yeah. Okay.
Sorry about that.
It's all right.
Any other questions or comments? Or you can just contact me via email.
So Ben, I'm trying to think about your work kind of in relation to some of the other talks we've heard this morning about effectively incorporating physics and other domain-based models as as constraints for loss functions and so forth. So is there a way in which kind of that approach sort of fits directly within your framework, or should we think of it in a more kind of modular way?
I would say it would, in many cases, it would be a trivial extension, because as long as we have as long as we already had a good understanding of the engineering and the scientific problem, we should be able to simply add a lot of like components in the search space to either reduce the search space or enlarge the search space. And based on the search space, we can just we can simply convert this problem from a manually tuning problem to a search problem for identifying a good machine learning solution towards a specific application.
Okay.
Yeah, and it's not too difficult to just formulate a lot of search components by converting those scientific functions. Yeah, in some cases, because we have been working with some of the collaborators towards this end, but we haven't had a lot of significant results yet, but I do see a lot of like promising results coming up very soon. Yeah. Okay.
Okay, thanks very much. Are there any other questions? Okay, well, thanks, Ben. We're going to take a very short break now until the top of the hour.